Hello everyone, my name is Chen Zekai, and I'm from Fuzhou University. I'm honored to have chance to address you on this special occasion. The topic of my paper is Privacy-Preserving Computation Toolkit on floating-point numbers. The outline of my talk as follows. The first part is some background information about this research. The second part, I want to introduce the system architecture and the basic definitions. The third part suggests privacy-preserving floating-point number computation protocols. In the fourth part, we introduce experiment and analysis. Finally, a simple conclusion is given. Nowadays, local users can't afford such a large amount of data computing. More and more enterprise customer applications, such as Internet of Things and self-driving cars, they need to be deployed in data center or cloud. Meanwhile, computation outsourcing using virtual environment is getting more and more prevalent in cloud computing, which several parties want to run a joint application and preserve the privacy of data in secure computation protocols. However, it is still a challenging task to improve the efficiency and the speed of secure floating-point calculation in computation outsourcing, which has efficient secure integer calculation. In related work, Zheng presents a secure integer division protocol that outputs as approximate quotient based on homomorphic encryption. Meanwhile, existing secret computation with floating-point number based on homomorphic encryption can be realized at huge computation costs and communication overhead, and the security division protocol isn't implemented. However, the above method can't solve the problem of secure floating-point number division and base operations on secure floating-point numbers in the current cloud outsourcing. Therefore, in this paper, we propose a framework built out with a privacy-preserving computation toolkit with floating-point numbers. In our paper, contribution we has as follows. First, secure floating-point number computation. The toolkit offers multiplication, addition, subtraction, division with floating-point number, which is trivial extension of the integer operations. Meanwhile, we present new protocols for the division of floating-point number. Second, multiple users. It has convenience and cost-effectiveness in supporting multiple secret keys in computing. Third, efficiency and accuracy. Our calculation toolkit equips with secure and efficient encrypted floating-point number, and our scheme has high efficiency and lower accuracy loss. In our toolkit, we introduce system architecture and base definition. First, two trapdoor crypto system, which split a private key into different shapes, secret key 1 and secret key 2, which can distributed decrypt ciphertext by secret key 1 and secret key 2 to get plain text. Second, Liu assumed there exists a semi-honest cloud server (CP) Computer Service Provider (CSP), and CP has private key secret key 1, and the CSP has private secret key 2. So, we present floating point number as U, which can be consist of mantissa-based exponent, and we can convert the mantissa into an integer. Meanwhile, encrypted floating point number can represent in encrypted mantissa base and encrypted exponent. All of the privacy-preserving multiple keys integer protocols are considered under CP and CSP. In secure addition, the goal of secure addition is to return the encryption of A plus B to CP, and input data covered by the random number is calculated in plaintext by CSP, and then returns to CP to minus cover random number. In this way, we can realize the ciphertext addition. In secure multiplication, we also can easily realize the ciphertext multiplication. The input data covered by the random number is calculated in plaintext by CSP, and in CP, receive CSP's encrypted data minus covered random number. At the same time, secure greater than, we flip a coin to compute encrypted 2 times A multiplied encrypted 2 times B plus 1 to the power n minus 1, or encrypted 2 times B plus 1 multiplied by 2 times A to the power n minus 1 to get the result of relationship between A and B. Meanwhile, secret maximum, secure exponent calculation, and the secure for CP can be solved in this way. In our system model and the thread model, system model is comprised of 4 kinds of entity, namely a center server (CP), computer service provider (CSP), multi-participant (MP), and the key generation center (KGC). And the CP and CSP is a semi-honest model, which is strictly follow protocol, but are also interested to learn data belonging to other parties. But are also interested to learn data belonging to other parties. In our toolkit, we propose a set of protocols which is used in cloud computation. All of the below protocols are under semi-honest parties. During the secure floating point number addition protocol, we use the secure addition, secure multiplication, secure exponent calculation, secure for CP protocols. It easily aligns to encrypted data of exponent part. Meanwhile, secure addition might be used to add two encrypted numbers of mantissa to get a result. At the same time, we can realize secure floating point number multiplication, which based on secure multiplication and the secure addition protocol. And we multiplied the encrypted mantissa part by secure multiplication protocol, and at encrypted exponent part by secure addition protocol. In secure digits protocol, the goal of this protocol is to compute the decimal digits of encrypted number, and we can calculate d equaled logis n to the base 10 after loading up +1 to get decimal digits. Therefore, we should solve the problem that how to compute logis n to the base 10 in secure by secure greater than and the secure exponent. During the secure modular calculation, given two encrypted integer number, we can get division, quotient, and the remainder. To start with, CP computes decimal digits of encrypted F1, encrypted F2 to get terms of loop body is executed. Then, using the secure greater than, secure maximum protocols, CP computes base number with the help of CSP from 1 to 9 to find the quotient and remainder. By assuming the number of quotient at each position to get encrypted Q and encrypted R. During the secure floating division protocol, the base idea is based on the follow property. We can use secret modular calculation to get encrypted quotient and remainder. In order to get higher precision, using the secret modular calculation protocol, CP computes encrypted Q1 and encrypted R1 of modular U and magnitude V. So we note U over V equaled Q1 plus R1 over V. Approximate Q1 plus Q2 times 10 to the power minus 17. So, and then encrypted R1 multiplies 10 to the 17, 10 to the power 17 do similar step to get encrypted Q2 and encrypted R2. Observe the value of R2 is very small. Ignoring doesn't affect accuracy. Meanwhile, we conduct experiments to show the performance of the proposed for evaluating our toolkit. Compared to with Liu, we can see the ABC in figure. Our secure floating-point number addition and the secure floating-point number multiplication have less computation cost and less joint computing time. But in our secure floating division, we can see D and G in figure. We can know that as the accuracy increases, the calculation time required for the division also increases. When the divisor is encrypted and the dividend is an integer or encoding number in DEFGHI, we can get the computation cost only in CP. This reduces the risk of the ciphertext leakage. And the terms of cost shown in table. We know that existing floating-point number division is constantly approaching result of division or obtaining the quotient and the remainder of division. In terms of precision, it is impossible to guarantee the precise range stably. However, our toolkit has higher precision in secure floating division. and the precision can be guaranteed at least 10 to the power minus 17. In conclusion, we propose Toolkit, which offers floating-point number multiplication, addition, subtraction, division. Meanwhile, it has security, efficiency, and accuracy. However, our limitation is the division communication time in CP is still worth optimizing and the high division accuracy but low efficiency. That's all. Thank you.